Okay, so in this particular video, we're going to be reviewing acid-base chemistry. And I think a good place to start would just be what are our definitions of acids and bases. And in this video, we're going to be going through protic acids, not Lewis acids. We'll discuss Lewis acids, as we get to them. But for this video, I kind of want to focus on what are acids, what are bases, and basically how can we tell their strength. So what are acids and bases? We have two definitions. And the first one, if you remember from Gen Chem, is our Arrhenius definition. And it's basically just saying that an acid is a species that makes the hydronium ion, and that a base is a species that makes hydroxide. And our other definition is the Bronsted-Lowry definition. And that is that an acid is going to be a species that donates a proton. So a proton we indicate is just H+. So we have a proton donor. And a base is a proton acceptor. All right, so let me give you a few examples here. For an acid, just a simple example, we have HCl. I'm going to leave off the physical properties just to keep it clean. We'll mix this up with some water. It will become what we call hydrochloric acid. On the other side, after we've donated a proton, so the color you can see here, we're going to be donating a proton here to the water. We're going to make the hydronium ion, and then we're also going to make what's called the conjugate base of the acid. So this will be the acid. This will be its conjugate base. You have to be mindful that these conjugate pairs are always present. You have an acid, after it's done giving up its proton, you will have its conjugate base. And the conjugate acid-base pairs differ by only one proton. So here we have a monoprotic acid, hydrogen chloride, right? Or in other words, when we mix it with water, hydrochloric acid. In this case, the water is going to behave as a base. So it's basically just going to be accepting the proton. And then over here we have its conjugate acid. We call that the hydronium ion. When you're measuring the pH of a solution, if you remember, you're measuring the concentration of the hydronium ion. For a diprotic acid, di means 2, right? Tri means 3. So for a monoprotic acid, we're good for donating 1 proton. For a diprotic acid, it's good for donating 2 protons, but they're not the same in terms of their strength. Once the first one is removed, the electron environment's a little different for the second. So we'll take something like sulfuric acid and realize that we're donating 1 proton at a time. So here's your acid. This is going to be the base. This will be your conjugate base. And this will be the conjugate acid. So theoretically, there's another acidic hydrogen on that conjugate base there. It can behave then as a monoprotic acid, and you'll donate another, right? But it goes one at a time. One proton is plucked off at a time. What about the bases? So we can take just our celebrity weak base, ammonia. We'll allow that to react with water. And it's weak, so I'm going to use this arrow. And we'll talk about weak versus strong in a sec. But essentially, we're going to be taking the lone pair of electrons on the nitrogen. I can draw them in just to make it a little more obvious. And those electrons are going to be used to take one of the hydrogens off of the water molecule. So this will end up being, as a base, a proton acceptor, and we're going to make the ammonium ion and the hydroxide ion. So here is the base, and now water is behaving as an acid. You might be wondering, how do you know when water can behave as an acid or a base? Well, you can pretty much mix any molecules together, and one can be the acid and the other can be the base, right? It's all a matter of a measure of their pKa, like how acidic are they, right? And so that goes again to acid-base strength, which we'll talk about in a sec. Here's going to be our conjugate acid. And this will be our conjugate base. So you get the idea. We're just transferring a single proton at a time. And I can put that over here. It's good to be mindful that these conjugate pairs or conjugate partners are going to differ by only one proton. Even if you have a polyprotic acid, only one proton is getting plucked off at a time. The acidity of each subsequent proton is going to be different. Okay, so let's jump into acid-base strength. And I've got a couple of different ways I'd like to share for how to assess this. And the first way is simply just qualitative. So by this I mean we're just going to look at the structure. So for example, with a simple binary acid, we'll start there, where you just have the acidic hydrogen and then one other atom. So we're going to look at the bond length, which is related to the bond strength or the bond energy. And this is where it's going to be helpful to lean back a little bit on some of the trends on the periodic table. In this particular case, we're going to lean on atomic radius. So it sometimes surprises students to hear that with binary acids, we're not going to be focusing on the electronegativity of the heteroatom. We're going to be looking at the size of the heteroatom and the length of the bond between that atom and the acidic hydrogen. Let me show you an example, and I'm going to exaggerate the length of these bonds. So fluorine, the atomic radius of fluorine is smaller than the atomic radius of chlorine. So we're just going to make a little bit longer of a bond there for the HCl, or between the HCl. Bromine is a little bit bigger than chlorine, so we're going to exaggerate this a little bit. And you notice that the bond length is going to be increasing as the atomic radius of the heteroatom increases. So for each of these particular molecules, we have a different bond length, and so we have a different bond strength. At the end of the day, what you're hoping for when you have a nice strong acid is that it's going to dissociate completely and fully protonate all of the water, right? So that whatever concentration of that particular molecule, HF, HCl, HI, whatever you got going on in there, whatever concentration you have is going to get fully transferred into hydronium ion, right, for a strong acid. With weak acids, they don't dissociate completely. And so at any given moment, you have in the pot at equilibrium a little bit of unreacted acid and then a little bit of its conjugate base with the hydronium ion. With a strong acid, it dissociates 100%, right? 100% ionization. And so at equilibrium, when you look in the pot, you don't have any acid left. So when we're staring at these binary acids, we're like, which one is going to be the strongest? Well, whichever one has the weakest bond. The longest bond is going to be the weakest bond, easiest to break, easiest to dissociate. So this is going to end up being your strongest acid of these choices. And this will be your weakest. So in other words, down here, I shouldn't say easiest, we'll say most complete. Most complete ionization or dissociation, whatever you want to call it. That bond will break, right? And the water molecule will get the proton. For the oxy acids, we're not just going to look at structure, but also the number of oxygen atoms. Oxygen is a pretty electronegative element, which means it has a tendency to hang on to its valence electrons pretty fiercely. It's also kind of interested in somebody else's valence electrons. So if they're sharing if oxygen is sharing electrons in a covalent bond, it's basically going to be hogging them, right? And so what that means is in an oxy acid, the acidic hydrogen, or the proton that's going to be taken off by the base, or the water in that case, right? When you put the acid into water, is going to have a greater partial positive charge if it's attached to a molecule with more electronegative elements on it. So the pull on the electron density in that that bond between the acidic hydrogen and its next element is going to be greater when the neighboring atoms are more electronegative. So for example, I could take acetic acid, and this is going to be our acidic hydrogen, and we're going to compare it to trifluoroacetic acid. In this case, we have the same number of oxygen atoms, but what we've done is we have increased the electronegativity of the neighboring atoms on trifluoroacetic acid. Fluorine is more electronegative than hydrogen, and so this will be a stronger acid. The partial positive charge on the acidic hydrogen is going to be greater, right? So they don't have an actual full-on formal charge of +1, but there's a fraction of a positive charge. And so we use that little delta symbol as our partial positive, right? Partial positive, partial negative, those symbols, familiar from Gen Chem. On trifluoroacetic acid, due to the increase in electronegativity of the neighboring atoms, so the fluorines that have been added to replace the hydrogens on acetic acid, all of a sudden now there's a greater pull on the electron density between the oxygen and the hydrogen. I can draw the bond in here if you like. So those electrons right there that are bonding that hydrogen to that oxygen, they're not being shared as evenly or as fairly, right, in those two different molecules. And so trifluoroacetic acid will end up being the stronger acid. We have a stronger or a greater partial positive charge on the acidic hydrogen. It's easier to remove, or it's more likely to dissociate completely or more completely. You can look at an example where you have a different number of oxygen atoms. Like, for example, you could take sulfuric acid, and we can compare it to sulfurous acid. In the first molecule, you see that we have an extra mole of oxygen atoms for every mole of sulfuric acid, compared to sulfurous acid, where there's only 3, right? In sulfuric acid, we have 4 moles of oxygen atoms. Oxygen is a pretty electronegative element, and so our acidic hydrogen, and I could have picked the other one as well. Doesn't matter, they're both diprotic acids, right? But we're going to lose one proton at a time, or one acidic hydrogen is going to be removed at a time. And on sulfuric acid, since we have more oxygen, there's a greater partial positive charge on the acidic hydrogen, and so that will be our stronger acid. So that's a qualitative assessment of our acids, right? And just looking at their structure. We can do the same thing with the bases. So in Gen Chem, we spend a little more time with acids than we do bases, but here I'd like to sort of jump in and describe. So how do we, okay. For the bases, let me label this for you. So up here, we're going to do acids first. And down here, we'll do bases. So I can do it qualitatively, just like I did with the acids. I'm basically going to be asking myself, what is the definition of a base? And that's going to be an important thing in this class anyway. So the difference between what we're going to call a nucleophile, the thing with electrons that's going to be attacking the thing that's deficient in electrons, and a base, because a base can be used as a nucleophile. So then what is the definition of a base? Well, we just talked about the Arrhenius definition and the Bronsted definition, but we can say, in general, a base is going to be, or a measure of basicity, right? In terms of like how awesome you are if you are a base. Basicity is a measure of how readily a species can remove a proton from another compound. So we're looking for, in general, a compound that has an element with a lone pair of electrons that can be used to grab an acidic hydrogen from another molecule. So the basicity in general is a measure of how readily a species can remove a proton from another compound. And so when we're looking at the strength of the base, we can lean back a little bit on some intermolecular force conceptual material from Gen Chem, namely our dispersion forces. So those were considered to be our weakest intermolecular forces of attraction. In organic chemistry, especially in this class, the bases that we're going to be using most often are either our oxygen containing bases, so some, molecule that has been deprotonated and now the oxygen has a negative charge, some oxide of sorts, right? A hydroxide or a methoxide or an ethoxide or something like that. Or we could be using nitrogen containing bases. Both nitrogen and oxygen are going to be hanging on to non-bonded electrons, and those are the electrons we're going to use to snag an acidic hydrogen off of another molecule. So how can you tell how strong your base is just by looking at it? Well, you could look at the structure and you're going to be asking yourself, hey, what would cause the lone pair of electrons on this base, since we're measuring how readily this particular species is to remove an acidic hydrogen from another compound, how available are the lone pair of electrons on that base, or how localized, right? How concentrated on the nitrogen are those electrons to do the attacking of the proton from another molecule, right? So if we're going to look at, for example, ammonia, so we have a lone pair of electrons on the nitrogen. We're going to be taking a proton off of water here, and we're going to be making its conjugate acid, the ammonium ion, and the conjugate base of water, which is hydroxide. But I can also compare this to another nitrogen-containing base, and now instead of 3 hydrogens bonded to the nitrogen, I'm going to substitute one of those hydrogens for another group. And that other group, I'm just going to keep it simple and use our smallest organic group. So organic means carbon containing. Our smallest organic group is the methyl group. Meth means 1, so 1 carbon. That carbon's actually bonded to the nitrogen. And I swapped out one of those hydrogens, and I've made methylamine. I'm going to put this into water. And you can tell by the arrow here. So when I have a weak acid or a weak base, I use those little equilibrium arrows. That's telling you that, at equilibrium, you're going to be finding some of your starting material unreacted. When you have a strong acid or a strong base, we typically will use that one arrow, that single-headed arrow that's going in the direction from reactants to products. So at what that kind of tells you sort of illustratively is that at equilibrium, you're unlikely to find any of your starting materials left over. They've all turned into products. And just like the other reaction, we're adding 1 proton at a time. So there's a lone pair of electrons on that nitrogen, methylamine. And after it has removed an acidic hydrogen from the water molecule, because water will behave as an acid in the presence of methylamine as well, we have its ammonium compound and hydroxide. So now which one is the stronger base? Well, I've indicated to you that methylamine is the stronger base by just showing you these different arrows. But how did I know that? In what molecule, ammonia or methylamine, are those electrons, those non-bonded electrons, more localized on the nitrogen, or in other words, more available to be used to take hydrogen off of the water molecule. And so what we're going to do is just kind of look at the difference in the dispersion forces, right? What is a dispersion force? Again, it's basically just a fleeting, sort of instantaneous dipole that occurs when the electrons in the species all kind of scurry over to one side and create a partial negative charge on that one side where they've gone to. Where they have come from now is electron deficient, and there's a partial positive charge. And you can increase the significance. So they're weak intermolecular forces of attraction, but you can increase the significance of them by increasing the number of polarizable electrons. The more mass you have associated with your molecule, the more significant the dispersion forces will be. And when we're looking at basicity, we're looking at dumping most of that partial negative charge onto that nitrogen, localizing those electrons in that spot, right? Or imagining so, anyways. What you don't want to do is add mass and electronegative character to the molecule. So I don't want to put a CF3, right, attached to that nitrogen. We'll be sucking electron density away from the nitrogen. We want to help pour electron density into the nitrogen. This is called an inductive effect, right? Where these electrons are sort of like imagined to be sort of streaming in toward the nitrogen, helping sort of bolster that partial negative charge, and making that lone pair sort of juicier for attacking an acidic hydrogen on another molecule. So when you're looking at the structure of a base and you're trying to decide which one is more basic, in general, if you don't add electronegative elements, if you add more substituents, that is, more groups on the atom that bears the lone pair of electrons. So in this class, we're mostly going to be dealing with nitrogen and oxygen atoms in that case. The more substituents you add, the better you are to localize the lone pair of electrons on the nitrogen, or if you had oxygen, on the oxygen atom, and you'll make that molecule more basic. So that's it for our qualitative assessment. Let's look at how we can quantify this. So we can look at acidity and basicity quantitatively. And what do I mean by that? Is that we're going to look at equilibrium data. In general chemistry anyways, often students are not sure why they're learning about things like Kas and pKas and Kbs and pKbs and all that stuff. And what is this equilibrium constant and why am I being forced to deal with it? Well, the equilibrium data gives us a picture of really what's going on with the reaction once the reaction has achieved equilibrium. When the reaction, and we're dealing with acid-base chemistry, has achieved equilibrium, the rate of the forward process, that is the ionization, right, or the dissociation of the acid, the rate of that equals the reverse rate, where the conjugate base and the conjugate acid would then react to give you your starting materials again. So at equilibrium, if you have more products than you have reactants, then chances are you had either a stronger acid or a stronger base in the reacting mixture. And the way that you can tell who is favored to be in greater concentration at equilibrium is looking at the equilibrium constant. So for example, with acid-base chemistry, we are going to look at Kas and pKas. Also, if you remember from Gen Chem, Kbs and pKbs. However, in this class, I'm probably going to stick to just talking about pKas. This is where you need to be mindful of the fact that these acids and bases exist as conjugate partners. So if I give you a pKa and you're looking at a base, you have to be telling yourself, wait a second, that's the pKa of its conjugate acid. And we remember that the stronger the acid, the weaker its conjugate base, and vice versa. So if you're dealing with a pKa that's really low, we have a stronger acid. If you're looking at a base and I give you a pKa, you have to say to yourself, she's talking about the conjugate acid. So if its conjugate acid is strong, then the base must have been weak. So let me show you just some illustrative examples of what I'm talking about. We'll start with a really strong acid. Really strong acids dissociate 100%. So we often don't discuss their pKa's because they're less than 1. But if this thing reacts with water, hydroiodic acid, we get the iodide ion and the hydronium ion. So there's the general reaction, right? Leaving off the physical properties anyways. And so the equilibrium expression for this, equilibrium expressions are indicated with a capital K. The little letter that comes after it is telling you what equilibrium process you're talking about. If you have a Ka, we're talking about the acid dissociation process. If you're talking about a Kb, right, we're talking about the reaction of a base with another molecule that's acting as an acid. If you're talking about like, you know, a gaseous mixture and you see a Kp, they're telling you that the equilibrium data was measured as a pressure sort of unit. If you see a Kc, they're talking about a mixture, usually an aqueous mixture or something like that, where you're dealing with a solution, and then they're talking about a concentration. If you see a little SP after the K, they're talking about a solubility product. So, but the capital K in general is talking about an equilibrium process. And so the K is a unitless, because this is a ratio, it's a unitless sort of comparison of our products and our reactants. So we're measuring who is present in a greater concentration once the reaction has achieved equilibrium. In this particular case, for any of these equilibrium expressions, we're talking about comparing the products to the reactants, and it's for those species whose concentration varies or can change. So if you're dealing with something with solids and liquids, we don't include those in the equilibrium expression because their concentration is constant. So in this particular case, I'm going to take my products. So I've got the conjugate base of my acid. Its concentration is going to be multiplied by the concentration of the hydronium ion. So those are my products. In the equilibrium expression, we usually raise these to the power of their stoichiometric coefficients, but this is all 1-to-1 mole ratios. So those powers will just be 1, and we don't write those in. And we're going to divide this by the concentration of the starting acid. Again, leaving the water out of it because its concentration is constant. So now, usually when you're given these values, these equilibrium constants, you get just a number, right? But so you have to be mindful of what this expression actually is telling you. You're looking to make this stuff, aren't you? From the acid. So if you have a large Ka value, what that tells you is since that's in the numerator, then at equilibrium, you have mostly products. So that's telling you in general, if you have a large Ka value, you had a really strong acid on the other side. The Ka value for hydroiodic acid is somewhere along the lines of 1 times 10 to the 9th. So a billion is a pretty big number. So just in case you're curious, what does a weak one look like? I can take acetic acid and I can put this into water. So see the difference in the arrow? That's telling you that at equilibrium, I have a little bit of my unreacted acid. And I have a little bit of the hydronium ion. And the Ka expression for this, same thing. Products over reactants. So this is just the general expression, right? And remember, if you remember from Gen Chem, when you did these calculations out, which by the way, in organic chemistry, you won't have to, I'm leading you toward looking at the value for us anyways, of the pKa. So to get a number for a pKa means something to us. We have to think back about what these expressions are actually describing. So, but with a weak acid, since they don't dissociate completely, if you remember when you're trying to calculate these values or get a pH out of this or whatever, if you have like concentration data to start with, we have to say, we're going to take that acid and we're going to subtract a little bit of it, right? Some of its concentration. So we could usually call it X is going to dissociate, but not all of it, right? So if you remember including that in your calculation, but the general expression is simply just the products over the reactants. And here, again, in the numerator, we see the hydronium ion. And so again, the larger the Ka value, the more hydronium ion you have at equilibrium. That gives you an indication of how strong the acid was or how complete the ionization was or the dissociation. So for hydroiodic acid, we saw a Ka value of 1 billion. With acetic acid, it's 1.75 times 10 to the negative fifth. So there's a huge difference in the value of the Ka, right? You can tell just by looking at those numbers that Ka value for acetic acid is so much smaller. And so that means that it doesn't dissociate nearly as completely as hydroiodic acid. And so that gives you an idea of how strong the acetic acid is compared to the hydroiodic acid. But here's the thing. Looking at these exponential numbers is kind of a drag. So numbers with exponents have a tendency to just, people just, start to gloss over. And that it doesn't feel very meaningful, right? It would be like if I said to you, hey, I have a glass of water and the concentration of the hydronium ion is 1 times 10 to the negative seventh. You'd be like, dude, what? But if I said to you, I have a glass of pure water and the pH is 7, your brain just goes straight to this little number line, doesn't it? And you can picture, oh, that's neutral, right? So like we have this idea about acidity and basicity based on our pH scale. That pH scale is based on the autoionization of water, which looks like this. So we're going to imagine that one of these water molecules is going to act as the acid and the other one's going to act as the base. And at equilibrium, we have some hydronium ion and hydroxide. For pure water, the concentration of each of these products has to be the same, doesn't it? Because it's water attacking water. The equilibrium constant for this particular reaction is going to be called a Kw, because we're just talking about the autoionization of water. The expression is the same, products over reactants, but the reactants are liquid. Concentration is constant. So the expression just looks like this. This is essentially over 1, right? And the concentration is the same. Each of these is 1 times 10 to the negative seventh. So the Kw is 1 times 10 to the negative 14th, And the pKw is going to be the negative log of the Kw, and so that'll just be 14. And in general, that's our upper end for our pH scale. And we usually go from 0 to 14, but you can go past 14 and you can go below 0. That's fine. This is just, in general, we have a little scale where we imagine acidity and basicity based around the pH, right? In other words, this could have been pH30 plus, but we abbreviate it just pH, is the negative log of the concentration of the hydronium ion. That's why you can't get a pH of something if it doesn't have any water. It doesn't make any sense, right? So if the concentration of the hydronium ion in pure water is 1 times 10 to the negative 7th, then the pH of pure water is just 7. So again, in Orgo, we're not going to be dealing with these calculations as much as we are with their relationships. So if you haven't noticed yet, that little p in front is indicating a logarithmic relationship for us. So if you have a Ka value of 1 times 10 to the 9th, you have a pKa is equal to negative 9. The negative log of the Ka is the pKa. Same like the negative log of the Kw is the pKw, and the negative log of the concentration of H3O plus is our pH, or pH30 plus, but nobody says that, right? We just say pH. pKa for acetic acid is 4.76. And these are easier to wrap your mind around, right? So when someone says to you, I have a pH of 1 versus a pH of 9, most people know that a pH of 1, if it's less than 7, right, you have an acidic solution. If it's greater than 7, you have a basic solution. So if I say the pH of my lemon water is, 1.2 or something like that, you're like, oh, that's an acidic solution. If I tell you that, the pH of blood is strictly maintained at 7.4 with a buffering system, in your body, then you're like, okay, that's a little bit basic, but only slightly so, right? Urine's like 8.2, right? So you have this sort of like vision in your head of what the acidity basicity is based on the pH. The smaller the p value was, the larger the value of the thing that we took the negative log of it was, right? So for example, if I'm talking about a smaller pH, then it means that the concentration of the hydronium ion was greater. If the concentration of the hydronium ion is greater, it must have come from a stronger acid. Does this start to make sense? So now when I say to you, the pKa of acetic acid is 4.76, and the pKa of hydroiodic acid is negative 9, you have it in your head like hydroiodic acid must be a stronger acid, right? So the smaller the pKa, the stronger the acid. The other thing we want to remember is that the stronger the acid, the weaker its conjugate base. And the same thing goes for bases, right? Because they're conjugate pairs. So if I'm talking about the strength of a base and I give you its pKa, I'm talking about its conjugate acid. If I give you a really low value for its pKa, that means it came from a really weak base. So this is in organic chemistry how we tend to make sense of the strength of an acid and a base, is generally just by looking at the pKa value. If you know you're looking at a base and I give you the pKa value instead of a pKb value, then you just have to imagine its conjugate partner and say, okay, the stronger the acid, the weaker its conjugate base. We also have this relationship, if it gets a little confusing. The pKw is equal to the pKa plus the pKb, right? So the pKa of the hydronium ion plus the pKb of hydroxide. pKa of the hydronium ion would end up being 7, and the pKb of hydroxide would end up being 7. And so this would end up being 14. So in general, if I give you a pKa and you're wondering like, okay, let me wrap my mind around the pKb, if that's more helpful to you, then just take 14 and subtract the pKa. You'll have the pKb of the base. Okay. So let's do a couple of examples. Basically, like how would these be presented? So types of problems, right? So types of questions that you might see. In organic chemistry, we're going to deal more with like leaving groups and nucleophiles and electrophiles and all that kind of stuff. We're going to be dealing with creating bonds and breaking bonds. And organic chemistry and synthetic organic reactions, we often have what's called a leaving group. If another group comes in and attacks a molecule, we have another piece of the other molecule that takes off. We call that the leaving group. The stronger the basicity of that particular group, the worse it is at leaving. So the other thing you want to keep in mind in organic chemistry is when we talk, or in chemistry in general, when we talk about the strength of something, we're talking about its reactivity. Reactions don't tend to produce more reactive products, right? They tend to produce products that are lower in energy, or they're more spontaneous, right? Thermodynamically, if they're, I guess, enthalpy wise, if they're exothermic, I should say, right? Or if we're going to increase the free energy of this, the product, then it tends to be more thermodynamically spontaneous, right? So what I'm saying is when you're looking at a molecule and we go to attack it and it has a group that takes off, the more reactive that leaving group is, the less likely that reaction is to occur on its own. So when we talk about, hey, that's a really strong base, it's a really crappy leaving group. Why? Because it's a really strong base. It's more reactive, or in other words, it's more unstable. So we have a tendency to use all those words synonymously. Types of questions that you might see. Well, for example, let's arrange. The following molecules. In order of increasing acidity. This is going to be one of those questions where you have those little greater than or less than symbols, right? So let's dream up some molecules here. I guess we could do this two ways. So let's make up, we're going to do it by pKa, and we'll do it by structure. So we can get a feeling for both methods, right? So one's off the top of my head. I've got acetic acid. And the pKa of that is 4.76. Trifluoroacetic acid is a pretty common organic acid. Now, just looking at the difference in structure there, we have a monoprotic acid for both, right? Everything else is the same, except in trifluoroacetic acid, I have added the more electronegative fluorines, right? So you expect the pKa to drop, right? The lower the pKa, the stronger the acid, right? Because the pKa is the negative log of the Ka. The larger the Ka, the more complete the dissociation. Do you see the relationship? 0.5 is the pKa for trifluoroacetic acid. Another weak-ish acid that I can think of is hydrofluoric acid. And the pKa for that, easy to remember, pi, 3.14. Carbonic acid is another one. So the pKa 1 for this, so this is a diprotic acid. The first pKa, there's two different pKa's, right? Once I take that first acidic hydrogen away, the other hydrogen that's left on its conjugate base is acidic, but it's not nearly as acidic. So the pKa 1 value for carbonic acid is 6.37. And then we'll take a strong acid where we've got a pKa that's less than 1. So it's like negative 1.5-ish for nitric acid. So now we're going to arrange these molecules in order of increasing acidity. So the one with the lowest pKa value gives you the highest Ka value, which means more complete ionization. So our strongest is going to be this one. Our weakest is going to have the highest pKa value. So our weakest acid has the highest pKa value, or in other words, the lowest Ka value, right? So now all you have to do is arrange these in order of increasing acidity. So you have to be mindful of this word. Sometimes it says decreasing. So increasing acidity means that the highest or the strongest acid is going to be on the right, and we're going to start with the weakest. So carbonic acid is the weakest. And if that's the weakest, we draw a little less than symbol. That means that carbonic acid is weaker than the next strongest acid, which would be the next highest pKa. That's acetic acid. And that's going to be weaker than our next strongest acid, which is hydrofluoric acid, which is going to be weaker than our next strongest acid, which would be, from this list, trifluoroacetic acid. And then that just leaves us with our strongest, which is nitric for this list. Another way we can do this, we can do it by structure. So if you're not given pKa values, I mean, you can always look them up, and we usually do. It's better to do things quantitatively, right? But qualitatively, if you're just in the lab and you're like, hey, I've got 3 acids. I've got, say, hypochlorous acid. I've got hypobromous and hypoiodous. And we're looking at these and we're saying, okay, well, who knows, right? The bond lengths are going to be a little different. So this is deceiving, right? Because you're looking at a situation where it looks like the hydrogen is actually attached to the halogen, but in reality, if you draw out the structure of these, the hydrogen is actually attached to the oxygen. So sometimes you might see these written like this. So in other words, the length of the bond between the hydrogen and the oxygen is the same for all of these molecules, but these hydrogens are not experiencing the same electron environment. The partial positive charge is going to be greater on the acid that has the more electronegative neighboring atom. So at the first point of difference is what I'm saying in these particular molecules is going to be the halogen. So this will be the strongest because the bond lengths are all the same. So I'll write that down here. HO bond lengths or strengths are the same, but you can write your little rationale down here. The electronegativity of the halogen are not the same. Chlorine's more electronegative than bromine, which is more electronegative than iodine. So the partial positive charge on the hydrogen will be the smallest on hypoiodous acid. So then just arranging these in order of increasing acidity, we start out with the weakest. And then we take the next strongest. And then the strongest. And that's about it. So that's the type of a question you might see. And you can ask the same types of questions for bases as well. You can use the pKa. If you use the pKa, imagine we're talking about its conjugate partner. If you use the structure, remember your dispersion forces. So if you're not adding electronegative elements onto the base, but you are adding groups, or in organic chemistry, we call them substituents. The more substituents you have on, say, a nitrogen, right? And that's in this class going to be, and if we're not dealing with a hydroxide of sorts or an oxide of sorts, then we're dealing with a nitrogen containing base. And in that case, we're saying, all right, how do we get those electrons on the nitrogen to be more localized? In other words, how do we juice up the electron density around the nitrogen so that we can use those electrons to attack a proton on a neighboring atom? And so if we add more groups and we don't put electronegative groups on those substituents, we add those to the nitrogen, then we increase that partial negative charge that can tend to build up in the direction of the nitrogen. And so you can assess the acidity or the basicity of a structure based on pKa, which comes from equilibrium data, or you could use structure.